My name is Rodrigo, and I'll be talking about the project I've been working on Argo, which is Core Solidity. We start by giving some context. Solidity is currently the most used smart contract language. It successfully secures billions of dollars in value. However, besides of its success, it has some limitations. The type system of Solidity lacks some expressivity. It's not able to allow us to define a reusable library code. And also the type system does not allow us to ensure certain safety properties. And also, Solidity does not have compile time eval. Currently, in the current implementation, we believe that adding a new type system, a more expressive type system, and compile time evaluation in the current implementation would be a lot hard. So, at Argo, we decided to rebuild the language type system and its compiler pipeline, and that's what we call Core Solidity. The type system will include a lot of new features that will make the language more expressive, and we also plan to develop formal semantics for the language in order to enable for static analysis and verification. What are these new features that we are planning? Basically, we plan to add generics and type classes from the audience who has a Rust background. Type classes are equivalent to Rust traits. We plan to add algebraic data types and pattern matching, also type inference, high order and anonymous functions, and compile time evaluation. The first feature that we start commenting is algebraic data types, which allow us to define data types using the concepts of sum and product types. And each algebraic data type defines a type name and a set of data constructors names. And these constructors can hold values that can be stored inside this type. As an example, we have here a data type for representing an 18 decimal fixed point numbers. Another example of algebraic data type is this data type for modeling an auction state. It has 4 constructors in order to represent different versions of the state of an auction. These different constructors represent the sum types and alternatives, which are basically different ways of building values of this type. The products can happen inside each constructor, and because each constructor can hold another tuple of different types, so we can, as an example here, the cancel constructor can hold an uint256 and an address as its arguments. However, the true power of algebraic data type comes when combined with pattern matching, which allow us to change the control flow of execution based on the shape of the matched values. Here, we have the definition of a type-safe multiplication function for this WOD data type. The pattern matching is made by a pattern match block, which should have a discriminant, which is the pattern which will be analyzed in this match block. Using the discriminant, we can then have a pattern describing its structure, and based on this pattern, we can introduce new values, new variables into context, which can be used to build a block for these values. In this case, we are building the multiplication of this function and return it inside the constructor of this type. Another nice feature that we are introducing in Core Solidity is the generics, or for people with a functional programming background, generics are also known as parametric polymorphism. The idea is that such feature allows us to define functions that will work in an uniform way for all types. Here we have the definition of an identity function which will work for any type T. In order to define the signature of this function, we first need to declare its type variable using the keyword for all, and then we can use this type variable in the whole definition scope. For instance, we are using here as a parameter type and also as a function return type. Also, generics allow us to define polymorphic data structures. For instance, here we have a data type which takes a type argument, which is a polymorphic type variable, which is used in the type constructor error in order to express the payload. Using this definition, we could reuse this data structure with any type expressible in the language. However, while interesting, generics are a bit limited because very few functionality works for all types. The most interesting functionalities work for some types. And that's why type classes come into play. Type classes are the standard solution to combine parametric polymorphism with function overloading. And here we have an example of a type class for defining a multiplication function. A type class defines a name of this type. For instance, here the name is mu. And also together with the name, we define a type argument. And in the body of the class definition, we define a set of function signatures which could mention the type argument which are defined in the type class. The implementation of a type class is given by an instance definition where the type argument of the type class is replaced by a concrete type. As an example, here we are implementing the type class for multiplication for the previously shown type of 18 decimal number fixed point, the WAD type. And in the definition of the instance, every place in the class declaration that we had a variable, a type variable, the type variable is replaced by the concrete type. So we have both in the function signature and in the instance argument, the type variable was replaced by the concrete type. And instead of having only the signature, the instance should provide the implementation of this functionality for this concrete type. One interesting feature is that we can, using type classes, we can define functions that allow us to restrict the set of polymorphic types in which the function can operate. As an example, we have here a function square, which will work for any type T which has an instance of this mu type class. We can restrict the set of possible polymorphic values within a function using a type class constraint. Here we say this type class constraint is specifying that this function would be valid for any type T which has an instance definition for the type class mu. Another interesting extension that we have in Core Solidity is that the language will now support both high-order and anonymous function. This means that functions are now a first-class syntax in Core Solidity, and they could be used as both function parameters and return values. As a short example of this, let's consider a simple utility which will allow us to count the number of calls a given function is called. Here, we are using inside this definition an anonymous function, We start the definition of an anonymous function using the lam keyword. After the lam keyword, we have the arguments of this anonymous function, and then its body. Anonymous functions can capture any values which are present in their definition scope. As an example, we can see in this function body that we have the definition of the counter variable, and it's mentioned inside the body of this anonymous function. So here we have a capture value for this anonymous function. And also, this utility shows an example. It serves as an example for high-order functions because it takes a function as argument and returns a function as a result. We use this syntax in which arguments are represented as a curried tuple, and the return type of the tuple of the function is marked by this arrow operator. Another interesting feature that we are adding to Core Solidity is type inference, which could be used to help the readability of programs, because we can use type inference in order to omit unnecessary type annotations, but also having the guarantee that all static checkings done by the compiler are done properly. Since we are dealing not only with parametric polymorphism, but also with overloading, some ambiguities can occur, but they occur in very rare situations when you are doing, for instance, some sort of type-level programming, which is possible within Core Solidity. As an example of the utility of type inference, let's consider this simple array literal definition in classic Solidity. This definition is rejected by the Solc compiler with an error message which says that the type uint8 is not implicitly convertible to uint256. In order to fix that, this happened because Solc uses a limited support for inferring the type of array literals. The idea is that the elements types of the array will have the type of the first expression such that all other elements can be implicitly casted to it. In this example, the first element has type uint8, so it considers that all elements have this type, and uint8 cannot be casted to int256 implicitly. The solution in classic Solidity is to add this type coercion into the first element of the array. However, in Core, this would work as it is, because thanks to the more general strategy used by the type inference, we can simply eliminate the need of this type coercion predicate. Okay, I showed several features that we are introducing in the language, but a question probably is remaining: how those features would help us to develop better code. Let's take a concrete example. Here is some snippets from the Forge std implementation of console.log utility. This implementation has a combinatorial explosion of overloaded functions. For instance, for logging one argument, we have more than 30 different function definitions. This happens basically because currently Solidity does not provide support for polymorphism. And in a simple way, all these more than 30 functions just call this one, which makes a static call to some specific address in order to implement the console logging. This same definition could be expressed in Core Solidity by just one single function. The idea is that thanks to type classes, we can restrict this function to receive only arguments that implement a type class for ABI encoding. So if any type has an implementation of ABI encoding, it could be logged without any problems. So basically, the code works as follows. We take the argument, ABI encode it to get its payload. Then we convert the payload to a representation which would be passed through assembly blocks, which inside Core Solidity is called the word type, which is basically a type which represents a U variable. So we convert it into a U variable and make the same assembly block to make the static call. So basically, the usage of type classes and generics allow us to reduce these repetitive definitions. Okay, but during the development of Core Solidity, it was clear that it would be really useful for us to add another mid-level IR, which is called SAIL, which stands for Solidity Algebraic Intermediate Language. It's basically a low-level language with some high-level features, like functions and low-level contracts, algebraic types and pattern matching, assembly blocks, type class and generics, variable introduction assignment, and a short-circuit if expression. The idea, one of the main motivations of Core Solidity was to make easy to extend the language. So in order to achieve this, we plan to use SAIL as the main definition language, and all Core Solidity high-level constructs would be desugared, translated into SAIL and standard library definitions. Such approach is used by several programming languages, several proof assistants, like the link prover, which also relies on several desugaring steps into a more verbose representation. The ultimate goal with this will be to allow us to extend both the language and standard library using some sort of RFC style process. Well, one thing that might be concerning the community is that we are planning a major review of the language, and this is a challenge thing. And we are really concerned to make this transition as smooth as possible to avoid a language split. So basically, our plan would be to keep the ABI compatibility. Also, we try as much as we can to minimize syntax changes. And we also are planning to develop tooling for automated migration from classic to core code whenever this migration is possible. As a concrete example, how core would be close to the classic Solidity, let's take the very first example of Solidity code which is present in Solidity documentation. It's basically a simple contract which defines a storage variable and get and set functions for it. The same code in Core Solidity would be exactly as this. The only syntax change would be that in Core we will use postfix types. And also we have a slight difference on the function signature syntax because we'll try to minimize this, to make the syntax of the prototype as simple as possible to start to develop the type theory and the type inference without bogus too much trouble with this, to replicate the syntax of function signatures in Solidity because they have a lot of stuff like function modifiers and stuff like that. So it's possible to see that the syntax is almost the same. Well, what remains to we reach production? We have a prototype implementation and also a prototype implementation of the standard libraries, which provides functionality for ABI-compatible contracts, ABI encoding and decoding, dispatch generation, and storage access. And our prototype is able to compile an ERC20 contract expressed using the standard library. Well, while we have done a lot of stuff, we have some steps that we need to finish. We need to define compile time evaluation and also a module system. Once we have these two features defined, we believe that we would have a stable prototype, and then once we have a stable prototype, we could split the development of Core Solidity in two fronts. The first one would be starting to produce a prototype implementation, and another one would be mechanizing the meta theory of the language use a proof assistant in order to have a verified semantics for it. This would be useful to, for instance, to fuzzing the compiler against its specification, which would be the meta theory of the language. Well, our focus would be to define the language as it was present here in the stock, but we have a lot of cool ideas that we want to explore in future iterations, like adding linear types, which would allow us to have compiler verified resource control, because it would be really useful in the context of Solid applications. Also refinement types, which will allow programmers to add logical properties to their code, which would be automatically verified. Since our objective is to make the addition of high-level constructs to Core Solidity to be implemented as the sugaring steps, one thing that we want to check how to include it in the language would be macros, because they allow us to implement new features, these sugaring steps, just as normal library code that could be imported, implemented it like in language like the Limprover or any Lisp dialect like Racket. And also, we would like to investigate how we could add theory-improving capabilities to the language following system language with these capabilities like Bedrock 2 or ATS. So basically, this is our Core Solidity, which is our reimagination of the language. All these changes aim to make the language more expressive, more secure, and mathematically sound. And that's it. Here is the QR code for the Solidity Core Solidity repository and for the feedback forum. And we love to hear your opinions on the language design and suggestions to help us to build the next generation of smart contract languages. Thank you.
Thank you so much, Rodrigo. We have quite a few questions, but luckily we also have some time reserved for these questions, so let's tackle them one by one. First question, why does the simple contract in Core Solidity need to import STD?
Because we need to generate the dispatch for this simple contract. So the dispatch generation is part of the standard library, is not part of the compiler itself, the compiler code itself. So a lot of the functionality which is currently built within the SolC compiler will be moved into the standard library of Core Solidity. This would help us and to make the language more extensible, because whenever the community wants to make a new addition to the language, we could just implement it as a part of the standard library without even touch the compiler source code. That's our ultimate goal.
5 people have voted already on these questions. What's the timeline or when Core?
That's a tough one because producing a new language like Core, it's not an easy task because we want to be sure that the type theory we are developing is sound and not incur in any unsoundness. So we need also to develop this thing of compile time evaluation that would demand a quite of time. It's quite complicated to give a precise timeline for that. Sorry.
I'd like to just chime in. We've been writing about Core Solidity and as well as Classic Solidity and the roadmap around it. These blog posts have been regularly coming out. We plan to write more about it, so please keep your eyes peeled for the upcoming blog posts in that series. That should also tell you a lot more about the team's progress with the new language and also like how we're making our way through the roadmap. It might not give the concrete timeline for the entire thing right away, but at least it will keep the community in loop. And I hope that answers the question a little bit. Moving on, are algebraic types going to be ABI encodable?
Yes. Yes.
Okay, yes is the answer.
Yeah, because ABI encoding would be implemented as part of the standard library, so any type that is defined in the language could be an instance of this type class for ABI encoding. Currently, we do not have this feature like language like Lean and Haskell, which supports type classes, has a feature which allows the automatically derivation of instances for newly defined algebraic data types. Our plan is to make, within the compiler, this automatic generation of ABI encoding through this deriving mechanism in a similar way which has happened within Haskell and Lean. But since it's part of a library, it gives the users the possibility to develop their own ABI encoding in a more efficient way if they want to, basically.
Awesome. Does Core Solidity also have the same caveats as Classic? Example, stack to deep errors during compilation.
Well, stack to deep is basically a problem of the backend. The Core Solidity is more concerned about the front end of the language, about the type system and the verification of, let's say, high-level constructs. Basically, this stack to deep error happens when all type checking and all verification of the code has already been done. So if it's a problem of the backend, well, Core is not able to solve it.
And what kind of features would make the language more secure?
Well, basically, when we have algebraic data types and pattern matching, we could allow a more precise representation of the types that are being used inside applications. This, thanks to pattern matching, could avoid issues like you have a gigantic struct which have a field to represent different situations. Like, for instance, you have an application that uses, let's say, 3 different kinds of tokens, and we use some field inside the struct to represent that a specific token value is being represented by this struct, and then you need to complicate a lot the logic for that. Also, having, let's say, a more type-safe language would allow the compiler to catch mistakes as soon as possible without having to the whole compilation pipeline. So in order, the plan is to make the language more secure, to make the type system of it more expressive. So we could express safety properties like making invalid array access and stuff like that represented within the types of the compiler itself.
This next question is a little less technical and more
Okay.
about the standard library. Who will be building the standard library? Will it be Argo? Will it be someone else? And will we have competing standard libraries like we have competing compilers and smart contract libraries?
The plan would be not having competing standard libraries. The idea for now is that we are the library we are building are basically as a test to assess how the language is how expressive is Core Solidity. So we may, using the language, we are able to define ABI encoding, dispatch generation, which are things which are basically implemented inside the Solidity compiler itself, and they are now in the user space, so it's possible to define it as you want using the language. This is a good sign of how the language is expressive. But the plan would be that, as I told in the talk, that both language chains and the standard library chains should be defined by the community using some sort of RFC style comments, that the community should prepare an RFC and some sort of committee decides if this would enter or not the standard library or the language itself.
Yeah. Do you have any plans to add higher kinded types?
Well, we would love to hear if you have some example of higher kinded types that would be useful. Please reach us with this example, because up to now we didn't see the need for higher kinded types. They are interesting, of course, but we are very cautious to not put too much type theoretical features in the language in order to make it as simple as possible.
I hope we're not wearing you out. It's clearly an important topic, so we have a few more questions. Do you have any idea if any LSP is on the works for supporting this new type system?
Whoa, no clue. I don't know if how much work would be involved in that.
Okay. Does the example of foundry polymorphism have zero additional gas cost compared to the current version?
Well, we do not measure gas costs. For now, we are making, let's say, experiments regarding on how expressive the language is. Basically, since Core Solidity will compile down to U, basically the gas costs would be similar, I would say, but we need to do some experiments to be sure on that. So we do not have data on this yet.
Okay. And are the data types just internal, or will we be able to use them when doing calls between contracts?
What? I do not understand.
Are the data types just internal, or will we
No.
be able to use them
Yes.
when doing calls between contracts?
Yes, would be possible to do it, because basically algebraic data types could live outside contracts. So you can have literally modules in the code which define functions and algebraic data types without being attached to a specific contract. So,
Okay,
yes.
awesome. And what are the gaps you see for Solidity to reach version 1.0?
It's a better question to be answered by Camille.
I was about to say that I think it's a Camille question.
Well, the main thing we need is stable implementation of Core Solidity, which means right now we have the Sol Core, the prototype. There are those things that Rodrigo mentioned, like modules in the prototype, like designing the compiler and evaluation system. This will complete the type system. Then we'll proceed to implement the kit in the SOC compiler. And there will be some period of stabilization. And 1.0, like as we stated in our blog post, is basically when the core is deemed stable enough, bug-free enough, feature-rich enough to become the default front-end. And then we'll, for a time, we'll have them side by side and eventually retire the classic Solidity. But for now, it's basically about when we'll get a stable production implementation.
Thanks so much, Camille. Not a question, please share the slides publicly. I just wanted to say that after every Solidity Summit, we basically, because all of the talks are recorded, we do publish the recordings along with the slides. So keep your eyes on the Solidity official blog. We will be publishing a blog post with a recap of Solidity Summit where you can find all of these slides that will be made public. And yeah, I think, okay, one more. Is it Haskell and Move that is inspiring these changes? And how long from production are we? That's also another question in the same vein as, is it 1 year or 5 years?
We took inspiration not only from Haskell, but also from Rust, which is quite popular among this blockchain domain. But surely Haskell is a great inspiration. And also the Lean language. So yes, Haskell, Lean, and Rust are the main inspirations for these new extensions to Core Solidity. Well, regarding the timelines, as I said, it's not easy because to be ready for production on this, we would like to have a formal proof that the type system we define is sound with respect to the semantics, and not just a pen and paper proof, because papers accept anything. So we would like to have a formally verified proof of this using some proof assistant. So it takes some time.
Thank you so much, Rodrigo.
Thank you.
That's all of the questions for you.